Before dinosaurs existed, most complex living things were found in the oceans. During the Devonian period, which lasted from about 419 million to 359 million years ago, sea life became much more varied and advanced. Big fish covered in armor-like body plates lived in the water, sharing the oceans with fast-moving predators. Early sharks also became more common during this time. Some of these sea animals grew very large with powerful jaws and sharp teeth that helped them catch prey. On land, simple plants and small animals were beginning to appear, but they were still few in number and not very diverse. Most of life was still in the seas, where many new species were evolving and adapting to different environments and ways of living. The Devonian period in Earth's history refers to a long span of geological time that took place during the Paleozoic era. This period began about 419 million years ago and ended about 359 million years ago. The total time covered by this period is about 60 million years. This span of time is used in geology and paleontology to describe a specific division of Earth's deep past based on rock layers, fossil records, and changes in life forms and environments recorded within those layers. The position of the Devonian period within the geologic timescale is set between the Silurian period before it and the Carboniferous period after it. These divisions are based on careful study of rock sequences found in many parts of the world. Scientists use fossils, chemical signals in rocks, and patterns in sediment layers to determine where one period ends and another begins. The boundaries of the Devonian period are defined by global changes, seen in fossils and rock formations that mark shifts in life on Earth and environmental conditions. The beginning of the Devonian period is placed at about 419 million years ago. This starting point marks a change in fossil records, where new types of marine life become more widespread and certain older groups become less common. The rocks formed during this time show a continuation of marine environments that were already present during the Silurian period, along with gradual changes in sea life diversity and structure. The early part of this period is often described in geological studies as the early Devonian, which includes the time from about 419 million years ago to about 410 million years ago. During the early Devonian, the Earth had large areas covered by shallow seas. These seas supported many types of marine organisms. Fossils from this time show the presence of different groups of fish, including jawless fish and early jawed fish. The structure of these fish is recorded in fossil bones, scales, and armor plates that are preserved in sedimentary rocks. Coral reefs also expanded during this time, and many reef-building organisms contributed to the formation of marine ecosystems that are preserved in limestone deposits. The rock layers from the early Devonian often include sandstone, shale, and limestone. These rocks were formed in environments such as river deltas, shallow seas, and coastal regions. The composition of these rocks provides information about the conditions present at the time they were formed. Fossils found within these rocks help determine the age of the layers and allow scientists to organize the Devonian period into smaller divisions based on biological and geological changes. The Middle Devonian spans from about 410 million years ago to about 398 million years ago. During this part of the Devonian period, marine environments continued to dominate large parts of the Earth's surface. Fossil records from this time show an increase in the variety of fish species, along with further development of coral reef systems. The structure of reef communities became more complex, with many different types of organisms living together in the same environments. The Middle Devonian rock record includes extensive limestone deposits that formed in warm, shallow seas. These limestone layers often contain fossils of corals, brachiopods, trilobites, and various types of fish. The preservation of these fossils allows scientists to identify the specific time intervals within the Middle Devonian. The arrangement of these fossils within rock layers helps establish a timeline for changes in marine life during this part of Earth's history. The Late Devonian begins about 398 million years ago and continues until about 359 million years ago. This final part of the Devonian period contains important changes in both marine and land environments. Fossil records show shifts in the types of organisms that were present in the oceans, along with changes in the distribution of species across different regions of the world. The Late Devonian is divided into smaller stages based on fossil evidence and rock formations that mark changes in environmental conditions. During the Late Devonian, certain intervals are marked by reductions in the number of some marine species. These intervals are identified through fossil records that show changes in biodiversity within rock layers. The Kellwater event is one such interval that appears in the fossil record and is associated with changes in marine ecosystems. Another interval, known as the Hangenberg event, appears near the end of the Devonian period and is also identified through changes in fossil patterns and sediment composition. The end of the Devonian period is placed at about 359 million years ago. This boundary marks a transition into the Carboniferous period. The rocks formed at this boundary show changes in fossil content and sediment structure. These changes are used to define the end of the Devonian in the geologic timescale. The boundary is identified in different parts of the world using standardized reference points called stratotypes, which are specific locations where rock layers clearly show the transition between periods. The time span of the Devonian period is measured using radiometric dating methods applied to volcanic ash layers found within sedimentary rock sequences. These methods involve measuring the decay of radioactive elements in minerals to determine the age of the rocks. By combining radiometric dates with fossil evidence, scientists establish a detailed timeline for the Devonian period. The integration of these methods allows the time span to be defined with a high level of consistency across different regions of the world. The Devonian period is part of the Paleozoic era, which includes several other geological periods arranged in a sequence of time. The position of the Devonian within this sequence is determined by changes in fossil assemblages and rock types that appear in different layers of Earth's crust. The study of these layers is called stratigraphy, and it provides a framework for organizing Earth's history into measurable time intervals. Stratigraphic records from the Devonian period are found on many continents, including areas that were once part of ancient landmasses. These records include marine sediment deposits, coastal formations, and terrestrial rocks that preserve evidence of environmental conditions during the Devonian. The distribution of these rock layers shows that sea levels changed during different parts of the period, affecting the areas where sediments were deposited. The early Devonian fossil record includes evidence of early fish diversity. Jawless fish were present in many marine environments, and jawed fish began to develop more complex structures. These fish are preserved in rocks as impressions, skeletal fragments, and mineralized remains. The study of these fossils provides information about the timing of biological developments within the Devonian period. Plant life during the Devonian period also expanded across land surfaces. The earliest vascular plants became more widespread, and their remains are found in sedimentary rocks from this time. These plants contributed to the formation of soil layers and influenced the development of terrestrial environments. Fossil spores and plant fragments are used to identify the presence of land vegetation during different stages of the Devonian period. The Middle Devonian fossil record shows continued development of marine ecosystems. Coral reefs expanded in shallow seas, and many marine organisms lived within these reef systems. Brachiopods, mollusks and trilobites are commonly found in fossil deposits from this time. The arrangement of these fossils within rock layers provides information about the structure of marine communities during the Middle Devonian. The Late Devonian fossil record shows significant changes in marine life distribution. Certain groups of organisms appear less frequently in some rock layers, while other groups become more common. These changes are recorded in sedimentary sequences that span millions of years. The study of these sequences helps define the internal subdivisions of the Late Devonian. Geological processes during the Devonian period include the movement of tectonic plates, which influence the formation of continents and ocean basins. These movements affected the distribution of land and sea, which in turn influenced sedimentation patterns and fossil preservation. Mountain building events occurred in some regions, leading to changes in rock formation and erosion processes. The climate during the Devonian period is studied through chemical signals preserved in rocks, such as isotope ratios and mineral composition. These signals provide information about temperature, ocean chemistry, and atmospheric conditions during different parts of the period. Changes in climate conditions are recorded in sediment layers that show variations in deposition rates and fossil content. The Devonian period also includes changes in oxygen levels in marine and terrestrial environments. These changes are inferred from rock chemistry and fossil distribution patterns. The presence of certain minerals in sediment layers provides evidence of oxygen conditions in ancient seas and soils. The study of the Devonian time span continues through analysis of rock cores, fossil collections, and global stratigraphic correlations. Rock cores taken from different regions are compared to identify matching layers of similar age. Fossil assemblages within these cores are used to align sequences from different locations into a consistent global timeline. The boundaries of the Devonian period are formally defined by international geological organizations that select specific reference sections in rock formations. These reference points are used to standardize the timescale across the world. Each boundary is marked by changes in fossil content and sediment characteristics that can be recognized in multiple regions. The internal subdivision of the Devonian period into early, middle, and late intervals is based on changes observed in fossil records and rock layers. Each interval represents a segment of time within the overall period, defined by patterns of biological and geological change preserved in Earth's crust. Sedimentary environments during the Devonian period included marine basins, coastal plains, river systems, and shallow inland seas. These environments produced different types of rock formations, including shale from fine sediments, sandstone from sand deposits, and limestone from marine organisms. Each type of rock preserves information about the conditions present at the time of its formation. Fossils from the Devonian period include remains of fish, marine invertebrates, early plants, and microorganisms. These fossils are distributed throughout rock layers that represent the full time span of the period. The study of these fossils allows scientists to reconstruct the sequence of events that occurred during the Devonian without introducing interpretive conclusions beyond the observed evidence in the rocks. The Devonian period time span remains an important part of the geologic timescale used to organize Earth's history into measurable segments based on physical evidence preserved in rock layers and fossil records spread across different regions of the planet. During the Devonian period, which took place from about 419 million years ago to about 359 million years ago, the arrangement of continents on Earth was very different from what exists today. The landmasses were not in their modern shapes and positions. Large portions of land were grouped into major continental blocks, and vast ocean areas separated these blocks. The surface of the planet showed a distribution of land and water that influenced climate, sea levels, and the development of marine and early land environments. The movement of Earth's crust over very long spans of time had already placed continents into broad assemblies, and these assemblies continued to exist through much of the Devonian period, with slow changes in their positions. At this time, one of the most significant continental groupings was a large northern landmass formed from earlier collisions of smaller continents. This landmass is often referred to in geological study as Laurussia or Euramerica. It included regions that would much later become parts of North America, parts of Northern Europe, and parts of Western Russia. These land areas were joined together through tectonic activity that had already occurred before the start of the Devonian period. The land within this northern assembly was positioned close to tropical and subtropical latitudes. Large portions of it were located near the equatorial zone of the planet. This placement created warm environmental conditions across many of its coastal and inland regions. The interior of Laurussia contained broad land surfaces that were exposed to air. These surfaces were shaped by erosion processes, sediment deposition, and slow geological uplift. Rivers flowed across these regions and carried sediments towards shallow seas located along the edges of the landmass. These shallow seas formed extensive marine environments that surrounded much of the continental margins. These marine zones supported large communities of marine organisms, including fish, early reef builders, and various invertebrate groups that lived in warm, shallow waters. To the south of Laurussia, another major continental block existed during the Devonian period. This southern landmass was known as Gondwana. Gondwana was extremely large and covered a wide range of latitudes across the southern part of the planet. It included areas that would later become South America, Africa, Antarctica, Australia, the Indian subcontinent, and Arabia. The land of Gondwana extended across polar regions and into temperate zones. Large portions of this landmass were positioned near the southern polar area of the Earth during parts of the Devonian period. Other regions of Gondwana extended toward warmer zones closer to the equator. The surface of Gondwana included a mixture of environments shaped by its wide spread across different latitudes. Some areas were exposed to cold conditions near the polar regions, where ice-related geological features existed during earlier periods and continued to influence land structure. Other regions experienced warmer climates and supported river systems, coastal plains, and shallow marine zones along the continental edges. The edges of Gondwana that faced surrounding oceans were active zones where sediment accumulation occurred and where marine ecosystems developed in shallow waters. Between Laurussia and Gondwana, a large oceanic region existed during the Devonian period. This ocean was known as the Archaic Ocean. The Archaic Ocean occupied a wide area and separated the northern continental assembly from the southern continental mass. The ocean floor contained spreading zones where new crust formed and subduction zones where older crust was recycled into Earth's interior. The boundaries of this ocean changed slowly over millions of years as continental plates moved and interacted. Sediments from surrounding landmasses were carried into the ocean through river systems and deposited along continental margins and deep ocean basins. The Reich Ocean contained island arcs, volcanic regions and deep marine basins. These geological features formed through tectonic activity along plate boundaries. Volcanic activity occurred in areas where oceanic crust interacted with other crustal sections. Island arcs developed in curved patterns above subduction zones. These islands contributed additional sediment and volcanic material to surrounding marine environments. The ocean supported a wide range of marine life, including fish, coral-like organisms, and other aquatic species that lived in different depths of water. Another major oceanic region present during the Devonian period was the Panthalassic Ocean, which covered a very large portion of the planet's surface. This ocean surrounded the major continental blocks and extended across vast distances. The ocean floor contained spreading ridges and deep basins shaped by plate movement. The edges of this ocean interacted with continental margins, where sediments accumulated and marine ecosystems developed. The Panthalassic Ocean contained a wide distribution of marine environments, from shallow coastal zones to deep ocean regions. Smaller oceanic regions also existed between different continental fragments and microcontinents. These smaller ocean basins were located in areas where crustal blocks had not yet fully merged with larger landmasses. Some of these smaller land fragments were located near the edges of Laurussia and Gondwana. These fragments gradually moved and sometimes collided with larger continents over long geological timescales. Their positions influenced the formation of mountain ranges, sedimentary basins, and coastal environments. During the early part of the Devonian period, the configuration of continents reflected earlier geological events from the Silurian period. Several smaller landmasses had already merged into larger units. The collision between Laurentia, Baltica, and parts of Avalonia had already formed the foundation of Laurussia. These collisions created mountain belts along the zones where the continents joined. These mountain systems affected the distribution of rivers and sediments across the interior regions of the landmass. The uplifted regions also influenced atmospheric circulation patterns at regional scales. Gondwana, during this same early phase, maintained its extensive size and continued to occupy large southern regions of the planet. Its internal structure included ancient cratons that were stable portions of continental crust. These cratons formed the foundation of present-day continental regions. The edges of Gondwana experienced tectonic interactions with surrounding oceanic crust. These interactions influenced volcanic activity and sediment deposition along coastal zones. As the Devonian period progressed toward its middle stages, subtle changes occurred in the positions of continental blocks. Laurussia remained positioned near equatorial latitudes and continued to experience warm environmental conditions across much of its surface. Shallow seas around its margins expanded and contracted due to changes in sea level and tectonic movements. These shallow seas played a significant role in marine biodiversity development during this time. Gondwana continued its broad distribution across southern latitudes. Its position extended from polar regions into warmer zones. The movement of this landmass occurred slowly due to tectonic plate motion. Different sections of Gondwana experienced slightly different movements depending on local plate boundaries. These movements influenced the shape of continental margins and the formation of sedimentary basins along the edges of the continent. The Reich Ocean remained a major separating body of water between Laurussia and Gondwana. Over time, parts of this ocean began to narrow, due to the gradual movement of continental plates toward each other. Subduction zones along the ocean margins consumed portions of oceanic crust. This process led to changes in the width of marine basins and the distribution of oceanic environments. Volcanic activity along these subduction zones continued to influence marine conditions and sediment composition. The interior regions of Laurussia contained extensive river systems that transported sediments from elevated regions toward coastal zones. These sediments contributed to the formation of delta systems and shallow marine deposits. The land surface included areas of erosion and deposition that shaped the geological structure of the continent. The presence of large shallow seas along the margins created extensive habitats for marine organisms, which contributed to the diversity of life during the Devonian period. Gondwana's interior regions included large stable crustal areas that experienced less tectonic disturbance compared to its margins. These stable regions preserved ancient rock formations that had existed for hundreds of millions of years prior. Along the edges of Gondwana, active geological processes shaped coastal environments. Rivers flowing across the continent carried sediments toward ocean basins, where they accumulated in thick layers over long periods. During the late stages of the Devonian period, the positions of continents showed continued slow movement toward configurations that would later become more recognizable in subsequent geological periods. Laurussia and Gondwana remained separated by oceanic regions, but the width of some ocean basins continued to change due to ongoing tectonic activity. The interactions between continental plates and oceanic crust continued to shape the distribution of land and sea. Ocean currents within these ancient seas were influenced by the arrangement of continents and the openings between landmasses. These currents affected the distribution of heat across marine environments and influenced the movement of nutrients within the oceans. Coastal areas along Laurussia and Gondwana experienced variations in sediment supply due to changes in river flow and sea level fluctuations. The continental margins of Laurussia included regions where shallow seas extended over parts of the land. These areas were covered by marine waters at different times due to changes in sea level and tectonic subsidence. The sediments deposited in these regions formed layered rock formations that preserved evidence of marine life and environmental conditions of the Devonian period. Gondwana's margins also experienced similar marine transgressions and regressions. Shallow seas periodically covered coastal areas, allowing marine sediments to accumulate. These sediments recorded changes in environmental conditions over long periods. The interaction between land and sea along these margins created complex geological structures that continued to evolve over time. The distribution of continents during the Devonian period also influenced atmospheric circulation patterns. Large landmasses positioned near the equator contributed to warm climate zones. The extensive southern continental mass influenced air movement across the southern hemisphere. The arrangement of oceans between continents allowed the movement of moisture and heat across different regions of the planet. Microcontinents and smaller crustal fragments existed in various oceanic regions. These smaller blocks of land moved independently and sometimes collided with larger continents. Their movements contributed to the formation of geological features, such as mountain belts and sedimentary basins. Some of these fragments were gradually incorporated into larger continental assemblies over time. The ocean floor between continental blocks contained spreading centers where new crust formed continuously. These spreading centers contributed to the expansion of oceanic crust in some regions and the reduction of ocean size in others, depending on the balance between creation and destruction of crust. subduction zones along continental margins recycled oceanic crust back into the mantle. The arrangement of continents during this period created a planet surface that included large continuous land areas in the south and a major continental assembly in the north. Between these landmasses, oceanic regions occupied large portions of the Earth's surface. These oceans contained diverse marine environments at different depths and temperatures. The interaction between continental positions and oceanic systems influenced geological processes across the planet. Sediment transport from continents to oceans played a major role in shaping marine basins. Rivers carried material from inland regions toward coastal areas, where it was deposited in deltas, estuaries, and continental shelves. These sediments accumulated over long periods and formed thick sequences of rock layers that preserved environmental records of the Devonian period. Tectonic forces continued to influence the positions of continents throughout the entire Devonian period. These forces operated slowly but consistently over millions of years. The movement of plates resulted in gradual changes in the shape and position of continents and ocean basins. These changes affected the distribution of land, sea, and marine environments across the planet. The overall arrangement of continents during the Devonian period reflected a dynamic Earth surface shaped by continuous movement of crustal plates, interactions between land and ocean, and long-term geological processes that operated across vast spans of time. The formation of the supercontinent Euramerica was a long geological process that took place over many millions of years during the late part of the Paleozoic era. It involved the slow movement of large sections of Earth's outer rocky layer, called tectonic plates, and the gradual joining of several continental landmasses that were once separated by wide oceans. These landmasses included Laurentia, which formed the core of what is now North America, and Greenland Baltica, which formed parts of northern Europe, and Avalonia, which included parts of what are now Western and Central Europe, as well as sections of Eastern North America. The joining of these landmasses happened through continuous movement driven by heat and convection inside the Earth's mantle, which caused the plates to move, come into contact, and eventually connect over long periods of time. During the early stages, the Earth's surface was divided into several large oceans and continents that were not connected. Between Laurentia and Baltica, there was a wide ocean known as the Iapetus Ocean. This ocean contained deep marine environments with thick layers of sediment accumulating on the ocean floor over long intervals of time. Avalonia was originally positioned near the northern edge of Gondwana, another large landmass located in the southern hemisphere during this period. Avalonia began to separate from Gondwana due to tectonic movement, and it moved toward the region where Laurentia and Baltica were located. This movement happened over tens of millions of years, with oceanic crust being created at some locations and destroyed at others through subduction processes, where one plate moved beneath another and entered the deeper mantle. As Avalonia moved away from Gondwana, the Rhyic Ocean formed behind it. This ocean expanded as the separation continued, while the Iapetus Ocean between Avalonia, Laurentia, and Baltica gradually began to shrink. The shrinking of the Iapetus Ocean occurred because oceanic crust was being consumed at subduction zones along the edges of Laurentia and Baltica. These subduction zones were regions where one tectonic plate moved downward beneath another plate into the mantle, causing the ocean floor to gradually disappear. Over long periods, this process reduced the width of the ocean basin and brought the continental edges closer together. Laurentia was located in the equatorial region during parts of this time, while Baltica was situated at different latitudes and gradually moved toward Laurentia due to plate motion. Avalonia, after separating from Gondwana, drifted across the shrinking ocean basin toward Laurentia and Baltica. The movement of these landmasses was slow on a human scale, but steady over geological time. The oceanic crust between them was continuously recycled into the mantle, and new continental margins were shaped by the forces acting at the edges of the plates. As Avalonia approached Laurentia, the first major contact zones began to form. These contact zones were regions where the edges of the continents started to press against each other. The sediment that had accumulated along the ocean floors began to deform under pressure, forming thick zones of folded and faulted rock. The pressure caused rocks to bend, break, and move upward in some areas, leading to the formation of early mountain belts. At the same time, Baltica was also moving toward Laurentia from another direction, and the closing of the Iapetus Ocean continued from multiple sides. The process of closure of the Iapetus Ocean played a central role in the formation of Euramerica. As the ocean narrowed, the remaining seafloor was pushed downward into the mantle through subduction. Volcanic activity developed along the edges of the continents due to melting of mantle material above the subducting slabs. Magma rose through cracks in the crust and created volcanic arcs along the margins of the converging landmasses. These volcanic arcs added new rock material to the edges of the continents and contributed to the thickening of the crust in those regions. The movement of Baltica toward Laurentia involved the gradual disappearance of oceanic crust between them. Sediments that had been deposited on the ocean floor were compressed and deformed as the two landmasses approached each other. These sediments included clay, sand, and organic material that had accumulated over long periods in the marine environment. As pressure increased, these materials were transformed into different types of sedimentary and metamorphic rocks through processes involving heat and stress deep within the crust. Avalonia eventually collided with Laurentia, first in several regions. This collision caused strong deformation along the edges of both landmasses. The crust in these areas thickened as rocks were pushed together and forced upward and downward. Fault systems developed where blocks of crust moved relative to each other due to stress. These fault systems allowed for the redistribution of pressure within the crust, and they played a role in shaping the evolving structure of the developing landmass. After Avalonia became attached to Laurentia, the combined landmass continued to move and interact with Baltica. The remaining portion of the Iapetus Ocean continued to close as Baltica approached the joined Laurentia-Avalonia landmass. This process involved continued subduction of oceanic crust and continued volcanic activity along the margins of the converging plates. As Baltica approached, sedimentary deposits along its margins were also deformed and transformed due to pressure and heat. The final closure of the Iapetus Ocean occurred when Baltica came into direct contact with the combined Laurentia-Avalonia landmass. This event resulted in extensive deformation of the crust along the collision zones. Rocks were folded into large structures, and deep sections of the crust were pushed upward to form elevated regions. At the same time, some portions of the crust were pushed downward and subjected to high pressure and temperature conditions, leading to the formation of metamorphic rocks. The joining of Laurentia, Baltica, and Avalonia formed a continuous landmass known as Euramerica. This landmass was positioned across regions that now correspond to parts of North America, Greenland, and Europe. The formation process involved the complete closure of the Iapetus Ocean and the integration of continental fragments that had previously been separated by oceanic basins. The crust in the newly formed landmass was thick and structurally complex due to the repeated episodes of collision and deformation. The development of Euramerica also involved the presence of other smaller terrains and microcontinents that were accreted to the edges of the larger landmasses during the collision process. These smaller fragments were carried by oceanic plates and attached to the growing continental mass when they reached subduction zones or collision boundaries. The addition of these fragments contributed to the complexity of the crustal structure and increased the diversity of rock types found within the landmass. During the formation process, the temperature and pressure conditions within the crust changed significantly in areas affected by tectonic activity. Rocks that were once formed at the surface or on the ocean floor were buried deep within the crust and subjected to transformation. These changes resulted in the formation of metamorphic rocks such as schist and gneiss, which developed from earlier sedimentary and igneous materials. Magmatic activity also continued in some regions where subduction zones remained active during the final stages of ocean closure. The structural development of Euramerica included the formation of large-scale fold systems. These fold systems developed when layers of rock were compressed and bent due to horizontal stress. The folding process affected sedimentary layers that had originally been deposited in horizontal positions on the ocean floor. As compression continued, these layers were deformed into complex shapes and structures that became part of the growing continental crust. Faulting processes also played a role in shaping the landmass. Faults formed when rocks fractured under stress and moved relative to each other along fracture surfaces. These movements redistributed stress within the crust and allowed for further adjustment of the landmass as collisions continued. Some faults were deep and extended through large sections of the crust, while others were more localized near the surface. The closure of ocean basins during the formation of Euramerica was accompanied by changes in the distribution of marine environments. As the oceans narrowed, marine habitats became restricted to smaller regions, and sedimentation patterns changed accordingly. Shallow marine environments developed along the margins of the closing ocean, where sediments continued to accumulate and were later incorporated into the growing continental mass through tectonic activity. The movement of tectonic plates during this time was driven by heat within the Earth's interior. This heat caused convection currents in the mantle, which created forces that moved the plates horizontally across the surface. These movements were continuous over long periods, leading to gradual changes in the positions of continents and ocean basins. The interactions between plates involved both creation of new crust at spreading centers and destruction of crust at subduction zones, maintaining a dynamic balance in the lithosphere. As Euramerica formed, the crust in the collision zones experienced repeated cycles of deformation. Rocks were subjected to stress, deformation, and recrystallization multiple times as different phases of collision occurred. These cycles resulted in complex geological structures that record the sequence of tectonic events involved in the formation of the landmass. The distribution of rock types across Euramerica reflects the different environments and processes that contributed to its assembly. The edges of Euramerica contained zones where oceanic crust had been fully consumed. These zones are marked by remnants of volcanic arcs, metamorphic belts, and folded sedimentary sequences. The presence of these features indicates the locations where subduction and collision processes were most active during the formation period. The internal regions of the landmass consist of older continental crust that had been part of Laurentia, Baltica, or Avalonia before their assembly. The process of assembling Euramerica also involved changes in elevation across different parts of the landmass. Areas affected by crustal thickening experienced uplift due to the accumulation of material and tectonic pressure. Other regions experienced subsidence where the crust adjusted to the added weight and structural changes. These variations in elevation contributed to the development of diverse geological settings across the landmass. Magmatic processes during the formation of Euramerica included the intrusion of molten rock into the crust. This magma cooled and solidified beneath the surface, forming intrusive, igneous bodies such as granite. These intrusions were associated with zones of tectonic activity and contributed to the thermal and chemical evolution of the crust. Volcanic eruptions also occurred in some areas where magma reached the surface through fractures and weak zones in the crust. The deformation of rock layers during continental assembly involved both brittle and ductile behavior, depending on temperature, pressure, and depth. Near the surface, rocks tended to fracture and break under stress, while deeper within the crust, rocks tended to flow and bend without breaking. These different behaviors contributed to the variety of geological structures formed during the assembly process. As the landmasses became fully connected, the internal structure of Euramerica continued to adjust. Residual stresses within the crust caused ongoing deformation even after major collisions had ended. Fault activity and minor tectonic adjustments continued in various regions as the landmass reached a more stable configuration. The crust remained thick and structurally complex due to the accumulated effects of long-term tectonic processes. Sedimentary basins developed in some regions of Euramerica, where the crust experienced downward bending. These basins collected sediments from surrounding elevated areas, and over time, these sediments formed thick layers of rock. The formation of these basins was influenced by tectonic forces, crustal loading, and thermal subsidence processes that affected the stability of the crust. The final arrangement of Euramerica represented the integration of multiple continental fragments and oceanic remnants into a single connected landmass. The structure of this landmass recorded the sequence of tectonic events that led to its formation, including ocean closure, continental collision, crustal deformation, magmatic activity, and sedimentary deposition. The processes involved continued over extended geological intervals, shaping the internal and external characteristics of the landmass as it developed. Climate conditions across the Devonian world were shaped by slow and continuous changes in the atmosphere, the oceans, and the land surface. These conditions were part of Earth's long history and were influenced by gases in the air, the movement of continents, the spread of seas, and the gradual rise of plants on land. During this long span of time, Earth's atmosphere held a high amount of carbon dioxide, and oxygen levels changed gradually as living organisms expanded in different environments. The air pressure, temperature patterns, moisture in the atmosphere, and circulation of winds all played roles in shaping how climate behaved across different regions of the planet. At this time, large areas of land were arranged in different positions across the planet. These land areas were not connected in a single large continuous block everywhere. Some were located closer to the equator, while others were placed closer to polar regions. Because of this arrangement, sunlight reached different parts of Earth in different ways, and heat from the sun spread unevenly across the surface. The atmosphere interacted with this uneven distribution of sunlight, creating zones of warm air movement and zones of cooler air movement. These air movements carried moisture from oceans and seas to land areas, shaping rainfall patterns and dry regions. The atmosphere contained a high concentration of carbon dioxide during much of this time. Carbon dioxide entered the air through volcanic activity, which released gases from deep within Earth. These gases accumulated over long periods because natural processes that remove carbon dioxide, such as plant activity and chemical reactions in rocks, were still developing. The presence of this gas influenced how heat from the sun was retained in the atmosphere. Heat energy absorbed during daytime hours remained present in the air and surface environments for longer periods, affecting daily and seasonal temperature changes. The balance between incoming solar energy and outgoing heat energy shaped the overall climate structure. Oceans covered a large portion of Earth's surface during this time. These oceans stored heat and slowly released it into surrounding air masses. Ocean water movement occurred through surface currents and deep water circulation. These movements transported heat and dissolved substances across large distances. Sea level changes occurred in response to changes in ice volume and the expansion of ocean basins. When sea levels changed, shallow seas spread across continental regions, creating environments where water temperature and salinity varied across different zones. These shallow seas also influenced humidity in nearby land regions by increasing moisture in the air. Land plants began to expand across many regions during this period. Early plant forms grew in moist environments near water bodies. These plants absorbed carbon dioxide from the atmosphere and released oxygen. As plant life spread, the composition of the air began to change gradually. This change influenced weather conditions because oxygen and carbon dioxide levels affect air density and energy exchange in the atmosphere. Plant coverage on land also influenced the movement of water through soil. Roots held soil in place, and this reduced the movement of loose particles during rainfall events. As a result, water movement across land surfaces became more structured, forming channels and small drainage systems. Rainfall patterns across the Devonian world were influenced by atmospheric circulation systems. Warm air near equatorial regions rose into higher layers of the atmosphere. As this air rose, it cooled and formed clouds. These clouds produced rainfall in cycles that repeated over time. Rainfall amounts varied across different regions based on proximity to oceans and seas. Coastal regions received moisture from ocean evaporation, while inland regions experienced drier air conditions due to reduced moisture transport. Seasonal variations in rainfall occurred due to changes in solar energy distribution over the planet during its orbit. Temperature distribution across the planet was influenced by latitude, atmospheric composition, and oceanic heat transport. Regions near the equator received continuous solar energy throughout the year, resulting in stable, warm conditions. Regions farther from the equator received sunlight at lower angles, affecting the amount of heat absorbed by the surface. Polar regions experienced extended periods of reduced sunlight, which influenced surface temperature conditions. These variations created zones of different atmospheric behavior, where air movement patterns and cloud formation processes operated in distinct ways. Wind systems played an important role in shaping climate conditions. Air moved from areas of high atmospheric pressure to areas of low atmospheric pressure. This movement created steady wind flows that transported heat and moisture across the surface. These wind systems were influenced by Earth's rotation, which caused air movement paths to curve. This curvature affected the direction of wind flow across oceans and land surfaces. Wind carried water vapor from ocean surfaces into the atmosphere, where it later condensed into clouds and returned as rainfall. This continuous cycle supported the distribution of water across different environments. Volcanic activity influenced atmospheric conditions during this period. Volcanoes released gases such as carbon dioxide, sulfur compounds, and water vapor. These gases entered the atmosphere and interacted with sunlight and cloud formation processes. Volcanic particles released into the air sometimes reduced the amount of sunlight reaching the surface for limited periods. This influenced short-term changes in temperature and rainfall patterns. Over longer periods, volcanic emissions contributed to the overall composition of the atmosphere and played a role in maintaining greenhouse conditions. The interaction between land and sea surfaces influenced local climate behavior. Coastal regions experienced regular exchange of heat and moisture between ocean water and air above land. Water evaporated from ocean surfaces entered the atmosphere and formed clouds, which later produced rainfall over land areas. This cycle created continuous moisture movement between ocean and land systems. Inland regions that were far from large water bodies experienced reduced access to atmospheric moisture, which influenced dryness levels and soil conditions. River systems transported water from higher regions of land to lower regions, contributing to the movement of sediment and dissolved minerals. Soil formation processes were influenced by climate conditions and biological activity. Weathering of rock surfaces occurred due to contact with water, air, and temperature changes. Over time, this process produced small particles that formed soil layers. Plants growing in these soil layers contributed organic material through decomposition. This organic material changed the chemical composition of soil and influenced its ability to retain moisture. Soil conditions varied across different regions depending on rainfall levels, temperature ranges, and vegetation coverage. The atmosphere during this period contained water vapor that played a key role in cloud formation. Water vapor originated from ocean surfaces, lakes, and wet land areas. When warm air rose, it carried water vapor upward into cooler atmospheric layers. In these layers, water vapor condensed into liquid droplets, forming clouds. These clouds moved across the sky with wind systems and released precipitation when conditions allowed. The distribution of clouds influenced how sunlight reached the surface and affected surface temperature patterns. Atmospheric pressure systems influenced climate conditions across different regions. Areas of high pressure were associated with descending air, which reduced cloud formation and limited rainfall. Areas of low pressure were associated with rising air, which increased cloud formation and rainfall activity. These pressure systems shifted over time due to changes in solar energy distribution and atmospheric circulation. The movement of these systems influenced seasonal patterns and local weather conditions. Chemical composition of the atmosphere played a role in determining how energy from the sun interacted with Earth's surface. Carbon dioxide and water vapor absorbed heat energy and contributed to warming of the lower atmosphere. Oxygen and nitrogen formed the majority of atmospheric gases and influenced air density and movement. Trace gases also contributed to atmospheric reactions that affected cloud formation and energy distribution. The balance of these gases changed gradually due to biological activity and geological processes. Large, shallow marine areas existed across many continental regions. These areas were influenced by sea level changes that caused water to spread over low-lying land surfaces. In these marine environments, water temperature, salinity, and oxygen content varied across different zones. These variations influenced chemical processes in the water, including mineral deposition and biological activity. The interaction between sunlight and shallow water influenced temperature patterns within these marine zones, affecting evaporation rates and cloud formation above them. Evaporation from ocean and sea surfaces played a central role in atmospheric moisture supply. Solar energy caused water molecules at the surface to gain energy and move into the air as vapor. This vapor accumulated in the atmosphere and contributed to humidity levels. Wind systems transported this moisture across regions, allowing clouds to form in areas far from original evaporation sources. This process maintained the movement of water through the atmosphere and influenced precipitation distribution. Lightning activity occurred within storm systems, formed in areas of strong atmospheric instability. These storm systems developed when warm, moist air rose rapidly into cooler atmospheric layers. The movement of charged particles within clouds created electrical energy that was released as lightning. These storm systems influenced local atmospheric conditions and contributed to chemical reactions in the air, including the formation of certain compounds that entered rainfall. Dust and fine particles in the atmosphere influenced cloud formation and sunlight scattering. These particles originated from volcanic eruptions, wind erosion of land surfaces, and impact events. When these particles entered the atmosphere, they provided surfaces for water vapor to condense. This process influenced the formation of clouds and precipitation patterns. The presence of airborne particles also affected how sunlight was distributed across the surface, influencing temperature variation during daytime periods. Seasonal cycles occurred due to Earth's movement around the Sun and its axial tilt. These cycles influenced the angle and intensity of sunlight reaching different parts of the planet. During periods when sunlight reached certain regions more directly, atmospheric warming occurred in those regions. When sunlight reached at lower angles, reduced surface heating occurred. These changes influenced wind patterns, cloud formation, and rainfall distribution across the planet. Seasonal variation affected both land and marine environments, shaping biological and chemical processes. Humidity levels across the Devonian world varied based on proximity to water sources and atmospheric circulation. Regions near large bodies of water contained higher amounts of moisture in the air. Inland areas contained lower amounts of moisture due to limited evaporation sources. Atmospheric circulation systems transported moisture between these regions, creating areas of cloud formation and rainfall. The movement of humid air influenced soil moisture levels and water availability in surface environments. The interaction between sunlight and atmospheric gases influenced energy distribution across the planet. Solar radiation entered the atmosphere and interacted with gases such as carbon dioxide and water vapor. Some of this energy was absorbed and retained in the lower atmosphere, while some was reflected back into space. The balance between absorption and reflection influenced surface temperature conditions. Cloud cover also played a role in this process by blocking or scattering incoming sunlight. Wind-driven dust movement affected land surfaces and atmospheric composition. Fine particles lifted from dry land areas were transported over long distances by wind systems. These particles settled in different regions depending on wind strength and atmospheric conditions. The deposition of these particles contributed to soil formation processes and influenced nutrient distribution across land environments. Atmospheric dust also interacted with sunlight, influencing visibility and energy absorption in the air. Water movement across land surfaces occurred through rainfall, river flow, and groundwater movement. Rainfall provided the main source of surface water input. This water flowed into rivers and streams, which transported it toward lower elevation areas. Some water entered the ground and moved through soil and rock layers. This underground movement contributed to the distribution of moisture across different regions and supported plant growth in areas with limited surface water. The composition of clouds influenced precipitation behavior. Clouds formed from water droplets and ice particles at different atmospheric levels. The size and distribution of these particles affected how and when precipitation occurred. When cloud particles reached certain conditions, they combined and formed larger droplets that fell toward the surface as rain. This process repeated continuously across different regions of the planet. Atmospheric circulation patterns included large-scale movement of air masses between different regions. Warm air moved upward in certain areas, while cooler air moved downward in others. This movement created circulation loops that transported heat and moisture across the planet. These loops influenced climate zones and weather conditions over long periods. The interaction between these circulation patterns and surface features such as oceans and land masses created varied atmospheric behavior across different regions. Cloud cover influenced surface temperature by affecting the amount of solar energy reaching the ground. When cloud cover was present, sunlight was scattered and absorbed within the atmosphere. When cloud cover was reduced, more direct sunlight reached the surface. This variation influenced daily temperature cycles and affected evaporation rates from water bodies and soil surfaces. Atmospheric chemistry also involved reactions between gases and particles. These reactions influenced cloud formation, rainfall composition, and energy absorption. Sulfur compounds released from volcanic activity interacted with water vapor to form aerosols. These aerosols influenced cloud brightness and lifetime. Carbon dioxide interacted with water in the atmosphere and contributed to chemical processes that affected rainfall composition. Moisture transport across the Devonian world depended on continuous evaporation and condensation cycles. Water moved from oceans to atmosphere, then to land, and then back to oceans through rivers. This cycle maintained the distribution of water across different environments. Atmospheric conditions controlled how quickly and where this movement occurred. Temperature, pressure, and wind systems all contributed to the movement of moisture through the air. Atmospheric stability influenced whether weather conditions remained calm or developed into storm systems. Stable air conditions reduced vertical movement of air, while unstable conditions encouraged rising air and cloud formation. These differences affected rainfall patterns and cloud development across different regions. Stability and instability changed over time due to variations in surface heating and atmospheric composition. The movement of heat energy across the planet occurred through radiation, conduction, and convection processes. Solar radiation provided energy input, while surface and atmospheric processes distributed this energy across different regions. Convection within the atmosphere moved warm air upward and cooler air downward, creating circulation systems that influenced weather patterns. Surface conditions on land influenced local atmospheric behavior. Areas with dense plant coverage affected air movement and moisture levels. Areas with exposed rock surfaces influenced heat absorption and reflection. These differences contributed to variations in local weather conditions and atmospheric circulation near the surface. Atmospheric oxygen levels continued to rise gradually due to plant activity. This increase influenced chemical reactions in the atmosphere and supported changes in biological activity on land and in water. carbon dioxide levels decreased gradually in some regions due to plant absorption and rock interactions. These changes influenced the energy balance of the atmosphere and affected climate conditions across different regions. Rainfall distribution influenced erosion processes on land surfaces. Water flowing across land carried small particles of rock and soil, shaping surface features over time. This movement of material influenced river formation and sediment distribution. River systems carried sediment into oceans and shallow seas, where it accumulated in layers on the seafloor. The interaction between atmosphere and surface water systems remained continuous throughout this period. Evaporation, condensation, precipitation, and runoff formed a repeating cycle that maintained water movement across the planet. Atmospheric conditions guided the intensity and distribution of these processes across different regions and time periods. Wind systems transported not only moisture but also heat energy across different regions. This movement influenced temperature distribution and cloud formation. Air masses moved across oceans and land surfaces, carrying energy that influenced atmospheric behavior in distant regions. Cloud formation processes depended on the presence of condensation nuclei, temperature changes, and humidity levels. Water vapor condensed onto small particles in the atmosphere, forming droplets that grouped together into clouds. These clouds varied in thickness and height depending on atmospheric conditions and moisture availability. Atmospheric circulation patterns influence long-term climate distribution across the Devonian world. These patterns were shaped by solar energy input, planetary rotation, and surface features such as oceans and land masses. The continuous movement of air masses maintained the distribution of heat and moisture across the planet without a fixed endpoint. Warm seas and widespread shallow oceans describe a long period in Earth history, when large parts of the planet were covered by water that remained near the surface of continents and continental margins, forming extensive, shallow marine environments. These seas were not limited to narrow coastal strips, but extended across broad areas of land that were low in elevation. Water filled these regions and created connected marine zones that covered vast spaces. The temperature of these waters stayed high over long periods, and this condition influenced many physical and chemical processes in the ocean environment. The presence of warm water across large regions affected how ocean water moved. Ocean currents in shallow seas were influenced by wind patterns, sunlight exposure, and the shape of the flooded land. Because the water depth was limited in many regions, sunlight reached the seafloor in many areas. This allowed continuous interaction between light, water, and sediments. The movement of sediments became an important part of the environment, as particles were constantly shifted by waves, tides, and slow water circulation. Shallow oceans formed across continental platforms, where the land surface was low and easily flooded. These platforms were wide and extended far inland in some regions. When water entered these areas, it created broad marine plains. The depth of water across these plains remained limited in many places, often allowing direct contact between ocean conditions and the underlying sediments. The structure of these environments allowed marine water to cover areas that today may exist as dry land or elevated terrain. The temperature of the seas remained high due to long periods of stable climate conditions. Solar energy reached the ocean surface consistently and heat was absorbed by the water. Because shallow water has limited volume, it responds quickly to heating. This allowed surface warmth to extend through much of the water column. Warm water conditions influenced chemical reactions in seawater, including the movement and concentration of dissolved minerals and gases. In these marine environments, evaporation played an important role. Warm water increased the rate at which water vapor entered the atmosphere. This process affected the balance of salinity in some regions of the shallow seas. In areas where evaporation was strong, dissolved salts became more concentrated. In other regions where freshwater input from rivers entered the sea, salinity levels remained lower. The mixing of these water types created zones with different chemical compositions. Shallow oceans also received large amounts of sediment from surrounding land areas. Rivers carried fine particles such as clay, silt, and sand into the sea. These materials spread across the sea floor and accumulated in layers over time. The constant movement of water in shallow regions allowed these sediments to be reworked repeatedly. Wave action could break apart sediment deposits and redistribute them across the sea floor. Tidal movement also contributed to this constant rearrangement of material. The interaction between warm water and sediment created conditions for chemical deposition. Minerals dissolved in seawater could settle out and form solid structures under certain conditions. These processes contributed to the formation of layered deposits on the sea floor. Over long periods, repeated deposition formed thick sequences of sediment. These sequences recorded changes in water conditions, sediment supply, and chemical composition of the seas. Light penetration into shallow oceans allowed photosensitive organisms to exist across large areas of the sea floor. The availability of sunlight in underwater environments supported energy production processes in organisms that relied on light. This extended the distribution of life across many regions of the shallow seas. The combination of warmth, light, and stable water conditions created environments that supported continuous biological activity. The physical structure of shallow seas included features such as broad platforms, gentle slopes, and slowly changing depths. These features allowed water to move without strong vertical mixing in many areas. Instead, water motion occurred mainly across horizontal directions, driven by wind and tidal forces. This movement distributed nutrients, oxygen, and dissolved materials across wide areas of the marine environment. Warm seas also influenced the behavior of dissolved gases in water. Oxygen levels in shallow regions were affected by exchange between the atmosphere and seawater. Because water depth was limited, atmospheric gases could enter and leave the water more easily. This exchange supported chemical balance within the marine system. Carbon dioxide also interacted with seawater, influencing chemical composition and supporting various chemical cycles. The structure of shallow marine environments allowed continuous deposition of carbonate materials in many regions. These materials formed through chemical precipitation processes in seawater. The presence of warm temperatures supported these processes by increasing reaction rates. Over time, carbonate-rich layers accumulated on the sea floor, forming extensive deposits. These deposits became part of the geological record of shallow marine conditions. The distribution of shallow seas across continents created environments where marine conditions extended far inland. In some regions, shallow water-covered areas that connected separate ocean basins. These connections allowed water movement between regions and influenced the distribution of marine conditions. The continuity of shallow seas supported the spread of similar environmental conditions across wide areas. The sediments within shallow seas contained particles of different sizes. Fine particles remained suspended in water for longer periods before settling, while larger particles settled more quickly. This created layering patterns in sediment deposits. Over time, repeated cycles of deposition formed sequences of layered material that reflected changes in water movement and sediment input. Warm, shallow seas also influenced the stability of chemical compounds in water. The temperature of seawater affected how quickly chemical reactions occurred. In warm conditions, reactions proceeded at steady rates, allowing continuous transformation of dissolved substances. This influenced the composition of seawater over long periods and contributed to the formation of new mineral deposits. In many shallow marine environments, water movement was gentle in some areas and more active in others. Regions closer to shoreline boundaries experienced stronger wave activity, while deeper parts of shallow seas experienced slower movement. This variation created differences in sediment distribution and water clarity across the marine environment. The presence of widespread shallow seas also affected the distribution of nutrients. Nutrients entered the ocean through river systems and were distributed across marine environments through water movement. These nutrients supported chemical processes that occurred in seawater and sediments. The circulation of nutrients allowed continuous interaction between land-derived materials and marine systems. In warm, shallow seas, the seafloor often remained within reach of sunlight for long periods. This allowed physical and chemical processes at the sediment surface to occur under illuminated conditions. Light exposure influenced temperature at the seafloor and contributed to ongoing chemical activity. Sediment surfaces experienced repeated cycles of deposition and disturbance due to water movement. The shallow ocean environment also allowed for frequent changes in water level in certain regions. These changes were influenced by tides, seasonal variations, and longer-term shifts in water distribution. As water levels changed, areas of the seafloor could become exposed or submerged repeatedly. This created dynamic conditions in coastal and near-coastal zones of shallow seas. Warm water conditions supported continuous exchange between ocean water and the atmosphere. This exchange influenced humidity levels above the sea surface and contributed to water vapor movement into the air. The movement of water between ocean and atmosphere formed part of the broader water cycle, which operated continuously across the planet. The shallow nature of these seas allowed sediments to interact closely with water chemistry. Dissolved minerals in seawater could combine with particles on the seafloor, leading to the formation of solid deposits. These processes occurred over long periods and contributed to the development of layered sediment structures. The interaction between chemistry and sediment dynamics was continuous in many regions. In many shallow marine areas, the seafloor consisted of soft sediment that could be easily reshaped by water movement. Waves and currents could form ripple patterns, channels, and other structures on the sediment surface. These features changed over time as water conditions shifted. The repeated reshaping of the seafloor created complex patterns of sediment distribution. Warm, shallow seas also allowed for strong interaction between biological and chemical processes. Organic material produced in the water column or on the seafloor became part of sediment deposits. As this material accumulated, it became incorporated into layers of sediment. The presence of organic material influenced chemical reactions within sediments and contributed to changes in composition over time. The distribution of shallow seas across continental regions created large connected marine environments. These environments allowed water to move across wide areas with relatively limited barriers. The connection between different shallow sea regions supported consistent environmental conditions over large distances. Water properties such as temperature and salinity remained influenced by regional conditions and local inputs. The chemistry of shallow seas was affected by the continuous input of materials from land sources. Rivers carried dissolved ions and particles into the marine environment. These materials contributed to the chemical balance of seawater and influenced sediment formation. The interaction between freshwater input and seawater created zones of mixing where chemical conditions varied. Warm, shallow seas also influenced the rate at which biological and chemical materials settled on the sea floor. Particles suspended in water gradually settled due to gravity. The rate of settling depended on particle size, water movement, and chemical conditions. Over time, this settling process formed continuous layers of sediment across the sea floor. The physical structure of shallow marine environments allowed sunlight to penetrate through much of the water column. This created conditions where the boundary between water and sediment remained active in terms of energy transfer. Heat from sunlight influenced both water temperature and sediment temperature. This energy transfer supported ongoing chemical activity in the shallow sea environment. In regions where shallow seas covered large continental areas, water circulation patterns developed based on the shape of the flooded land. Water moved through channels, across platforms, and around elevated areas of the sea floor. These movement patterns influenced sediment distribution and water chemistry. The shape of the submerged landscape played an important role in guiding water flow. Warm seas also influenced the solubility of gases in water. Oxygen, carbon dioxide, and other gases exchanged continuously between the ocean and atmosphere. In shallow environments, this exchange occurred efficiently due to limited water depth. The balance of gases in seawater supported chemical stability and ongoing reactions within the marine system. The repeated deposition of sediments in shallow seas created layered structures that accumulated over long periods. Each layer represented a period of sediment input and water movement. These layers formed sequences that recorded changes in environmental conditions within the shallow marine system. The accumulation of sediment continued across many regions where shallow seas remained stable. The warm temperature of shallow seas supported consistent chemical activity in seawater. Reactions involving dissolved minerals occurred continuously. These reactions influenced the composition of seawater and contributed to the formation of solid materials on the sea floor. The interaction between temperature, chemistry, and sediment processes remained active throughout the existence of these marine environments. Shallow seas also allowed for close interaction between water and the atmosphere. Wind influenced surface water movement, creating waves and surface currents. These movements transferred energy into the water column and affected sediment distribution in near-surface regions. The interaction between wind and water created dynamic surface conditions across the shallow marine environment. The structure of shallow marine environments allowed for the accumulation of fine sediments over large areas. These sediments were transported from land sources and distributed across the seafloor by water movement. The settling of these particles created extensive sediment layers that formed the foundation of the shallow seafloor. Warm, shallow seas provided conditions where chemical and physical processes operated continuously over long periods. Water movement, sediment deposition, gas exchange, and mineral formation occurred at the same time within these environments. The interaction of these processes created complex and active marine systems that extended across large portions of the planet's surface. Oxygen in the Devonian atmosphere refers to the amount of oxygen gas present in the air during the Devonian period of Earth's history, a long span of time that lasted from about 419 million years ago to about 359 million years ago. The atmosphere during this period was made of several gases, mainly nitrogen and oxygen. along with smaller amounts of carbon dioxide, water vapor, and other trace gases. Oxygen was one of the most important components because it supported the life processes of animals, plants, and many small organisms that were becoming more widespread on land and in water. At the beginning of the Devonian period, oxygen in the atmosphere is estimated to have been around 15% by volume. This level represents the proportion of oxygen gas in the air when measured out of the full mixture of atmospheric gases. Air at this time still contained a large amount of nitrogen, which formed the main part of the atmosphere. Carbon dioxide was also present in the atmosphere at levels that were higher than modern times in many regions and times within the Devonian, although it varied across different stages of the period. Water vapor was present depending on local climate conditions, evaporation rates from seas, and atmospheric circulation patterns. As the Devonian period progressed, oxygen levels in the atmosphere changed gradually over long spans of time. Around the middle part of the Devonian period, oxygen is estimated to have reached about 17% to about 19% by volume. This change in oxygen amount was linked to the expansion of plant life on land and the increasing spread of early forests, moss-like plants, and vascular plants that developed systems for moving water and nutrients. These plants carried out photosynthesis, a biological process that uses sunlight, carbon dioxide, and water to produce energy for the plant while releasing oxygen into the atmosphere. Photosynthesis by land plants contributed oxygen directly into the air above continents. At the same time, algae and other photosynthetic organisms in shallow seas also released oxygen into surrounding water and, indirectly, into the atmosphere through gas exchange at the ocean surface. The expansion of plant-covered land surfaces created more areas where oxygen could be released into the atmosphere over long time spans. These biological processes worked continuously during daylight hours, while at night respiration by organisms used oxygen and released carbon dioxide back into the environment. The Devonian atmosphere also experienced changes in the way carbon was stored in living systems and in sediments. Some organic material produced by plants and aquatic organisms was buried in sediments in wetlands, river plains, and shallow marine environments. When organic matter becomes buried and removed from immediate decay, the carbon it contains remains trapped for long periods. This process allowed oxygen produced by photosynthesis to remain in the atmosphere rather than being fully consumed by decay processes. Over long periods of time, this contributed to gradual changes in atmospheric oxygen levels. By the later part of the Devonian period, oxygen in the atmosphere is estimated to have reached around 20% to 23% by volume in some time intervals. This stage of atmospheric composition supported a wide range of animal life both in water and on land. In oceans, fish diversity increased significantly, including armored fish, early jawed fish, and early forms of sharks. These organisms depended on oxygen dissolved in water, which itself was influenced by oxygen levels in the atmosphere through gas exchange between air and ocean surfaces. On land, early arthropods, such as insects and myriapods, were present. These organisms relied on oxygen for respiration through specialized breathing structures, such as tracheal tubes. The amount of oxygen in the air affected how efficiently oxygen could move into their bodies through diffusion. Higher oxygen availability in air allowed these organisms to support their energy needs in various environments, including moist forest floors, swampy areas, and vegetation-rich habitats. Plant life during the Devonian period became more diverse and structurally complex. Early plants included simple vascular plants that grew in damp environments, followed by larger tree-like plants that developed woody tissues. These plants formed the earliest known forests in Earth's history. Forests created large continuous areas of plant cover, which influenced oxygen production on a global scale. The presence of roots in soil also changed how nutrients and carbon were cycled between land and atmosphere. Roots helped stabilize soil and allowed plants to grow larger and live longer, which increased the total amount of photosynthetic activity occurring on land surfaces. Oxygen in the Devonian atmosphere also interacted with other gases in chemical processes. Oxygen can combine with carbon to form carbon dioxide during respiration and decay. It can also participate in reactions with minerals exposed at Earth's surface. Weathering processes on rocks involved oxygen in chemical reactions that broke down minerals and released elements into soils and water systems. These processes contributed to long-term cycles that affected atmospheric composition. Volcanic activity during the Devonian period also influenced atmospheric gases. Volcanoes released gases such as carbon dioxide, water vapor, sulfur compounds, and small amounts of other gases into the atmosphere. While oxygen itself was not a primary volcanic gas, volcanic emissions influenced climate and environmental conditions, which in turn affected biological activity that produced oxygen. Periods of volcanic activity could change atmospheric conditions temporarily, but oxygen levels were mainly controlled by biological processes over long durations. The ocean surface during the Devonian period acted as an important interface between atmospheric oxygen and marine systems. Oxygen from the air dissolved into surface waters, supporting marine organisms that required oxygen for respiration. Ocean circulation patterns helped distribute oxygen within shallow seas. In deeper ocean regions, oxygen levels depended on the movement of water masses and the biological activity of marine life. Oxygen availability in marine environments played a role in the distribution and diversity of marine species. The evolution of fish during the Devonian period is closely connected to oxygen availability. Fish with more efficient respiratory systems could extract oxygen from water more effectively. Some fish developed stronger jaws, improved swimming abilities, and more active lifestyles that required sufficient oxygen supply. Oxygen dissolved in seawater came partly from atmospheric oxygen, which entered water through surface contact and mixing processes. Changes in atmospheric oxygen over long periods contributed to changes in marine ecosystems. On land, arthropods developed various forms of respiration adapted to atmospheric oxygen conditions. Some early insects had simple respiratory systems that relied on direct diffusion of oxygen through small tubes. The structure of these systems meant that oxygen availability in air was an important factor in their ability to move and feed. The spread of vegetation on land created humid environments that supported these organisms and provided shelter and food sources. Soil formation during the Devonian period also influenced atmospheric oxygen cycles. As plants grew and died, organic material accumulated in soils. Microorganisms in soil decomposed organic matter, consuming oxygen and releasing carbon dioxide. At the same time, plant roots transported oxygen into soil layers, affecting local chemical conditions. These interactions between soil processes and atmospheric gases formed part of the overall oxygen cycle. The Devonian atmosphere also experienced variations in oxygen distribution across different regions and environments. Coastal areas with dense plant growth and wetland systems likely had strong oxygen production due to high levels of photosynthesis. Inland dry areas may have had different balances of oxygen production and consumption depending on plant density and environmental conditions. Over long time spans, these regional variations contributed to the overall global oxygen pattern. In freshwater environments such as rivers and lakes, oxygen levels were influenced by both atmospheric exchange and biological activity within the water. Aquatic plants and algae produced oxygen during daylight hours, while animals and microorganisms consumed oxygen continuously. Water movement, temperature, and depth influenced how oxygen was distributed within these environments. Freshwater ecosystems supported a variety of early fish and invertebrates that depended on oxygen dissolved in water. The chemical composition of the Devonian atmosphere also included interactions between oxygen and ultraviolet radiation from the sun. Oxygen in the upper atmosphere could be affected by solar radiation, leading to the formation of ozone, a molecule made of 3 oxygen atoms. Ozone played a role in absorbing ultraviolet radiation, which influenced environmental conditions at Earth's surface. The presence of ozone depended on the availability of oxygen in the atmosphere and the energy from solar radiation. Over the course of the Devonian period, biological evolution played a central role in shaping oxygen levels. As plants expanded in size and diversity, they increased the total amount of oxygen produced through photosynthesis. As animals evolved more complex forms and increased in activity, they used oxygen for energy production through cellular respiration. The balance between oxygen production and consumption influenced atmospheric composition over long periods. The burial of organic carbon in sediments also played an important role in oxygen accumulation in the atmosphere. When organic matter is buried in environments such as river deltas, floodplains and shallow marine basins, it is removed from immediate decomposition. This process reduces the amount of oxygen consumed in decay reactions and allows oxygen produced by photosynthesis to remain in the atmosphere for longer periods. Over millions of years, this process contributed to changes in atmospheric gas composition. During different stages of the Devonian period, environmental conditions such as temperature, sea level, and continental positions influenced biological productivity. Warm, shallow seas covered large areas of continental margins, providing environments for marine life that contributed to oxygen cycling. Land areas experienced changes in moisture and climate patterns that influenced plant growth. These environmental factors indirectly affected oxygen levels through their influence on living organisms. Atmospheric oxygen during the Devonian period also influenced the development of fire as a natural process. Oxygen is required for combustion, and the presence of sufficient oxygen in the air allows plant material to burn when ignition sources are present. Evidence from later geological periods shows widespread fire activity when oxygen levels were sufficiently high. In the Devonian period, oxygen levels were part of the conditions that determined whether natural fire events could occur in vegetation-rich areas. The interaction between oxygen and other atmospheric gases formed part of a long-term chemical balance. Carbon dioxide levels influenced plant growth, which in turn affected oxygen production. Water vapor influenced climate conditions that affected plant distribution. Nitrogen remained relatively stable as a major component of the atmosphere. Oxygen gradually changed over long periods as biological and geological processes interacted. Microbial life in soils, sediments, and aquatic environments played a continuous role in oxygen consumption. Bacteria and other microorganisms broke down organic matter using oxygen in their metabolic processes. This consumption of oxygen was balanced by oxygen production from plants and algae. The overall atmospheric oxygen level resulted from long-term interactions between these biological processes. The Devonian atmosphere provided the environmental conditions necessary for the continued expansion of life on land and in water. Oxygen played a central role in energy production for living organisms through cellular respiration. In this process, oxygen is used inside cells to break down organic molecules and release energy needed for growth, movement, and reproduction. The availability of oxygen in air and water supported increasingly complex life forms. Over millions of years during the Devonian period, the continuous cycling of oxygen through photosynthesis, respiration, decay, burial of organic matter, and geological processes shaped the composition of the atmosphere. These processes operated across land surfaces, oceans, soils, and sediments in a connected system that maintained atmospheric balance over long time scales. The development of early coral reef systems was a long natural process that took place in the ancient oceans of Earth over a very large span of geological time. It involved slow biological growth, gradual changes in ocean chemistry, and the steady expansion of marine life forms that were able to build hard structures. These systems formed through the activities of small marine animals that lived together in large numbers and created solid frameworks on the seafloor. The earliest stages of reef development began hundreds of millions of years ago, when simple marine organisms started producing calcium carbonate structures that accumulated over time. These structures became stable surfaces that supported further growth and allowed more organisms to settle and live in the same areas. In the earliest oceans of Earth before the appearance of complex reef systems, marine life consisted mostly of simple organisms that floated in the water or lived on soft seafloor sediments. Over time, some of these organisms developed the ability to secrete mineral materials that formed hard external coverings or internal support structures. These mineral materials were mainly made of calcium carbonate, which is a compound found in seawater. As these organisms lived and died, their hard parts remained on the ocean floor. Over long periods of time, these remains built up in certain locations, creating stable foundations that allowed new organisms to attach and grow. The first coral reef systems did not appear in their modern form immediately. Instead, they developed through many stages involving different types of marine organisms. Some of the earliest reef-building organisms were simple coral-like animals that belonged to groups different from modern coral species. These early reef builders included small colonial organisms that lived together in clusters. Each individual organism within a colony contributed to the growth of the overall structure by producing mineral material. As colonies expanded, they formed larger and more complex structures on the seafloor. The process of reef development depended on environmental conditions in the ocean. Water temperature, salinity, depth, and the availability of sunlight all influenced the growth of reef-building organisms. Shallow marine environments were especially important because they allowed sunlight to reach the seafloor in many areas. Sunlight supported the growth of microorganisms that lived in association with reef-building animals. These relationships helped increase the rate of mineral production and contributed to the expansion of reef structures over time. During the early stages of reef formation, ocean chemistry played a central role. Calcium and carbonate ions dissolved in seawater combined under certain conditions to form solid calcium carbonate structures. Reef-building organisms used these ions from seawater to construct their skeletons. As more organisms lived in the same area, the amount of calcium carbonate accumulation increased. This led to the gradual formation of large reef systems that extended across wide areas of the seafloor in shallow marine regions. The earliest known reef systems appeared during the Precambrian and early Paleozoic intervals, when simple marine life forms dominated Earth's oceans. These early reef systems were not as structurally complex as later ones, but they established the basic biological and chemical processes that would continue for hundreds of millions of years. During this time, microbial communities also played a major role in reef development. Microorganisms formed layered structures on the seafloor that trapped sediments and contributed to the stability of early reef environments. As time continued into the early Paleozoic era, reef systems became more organized. The appearance of early corals and other skeletal organisms increased the rate of reef formation. These organisms were capable of building more rigid and durable structures compared to earlier microbial systems. They lived in colonies that grew outward and upward over time, forming elevated structures on the seafloor. These structures provided habitats for many other marine organisms, increasing biological activity in reef areas. The development of early coral reef systems also involved interactions between biological growth and sediment accumulation. Sediments carried by ocean currents settled in areas where reef organisms were present. Some of these sediments became trapped within the growing reef structures, while others were incorporated into the framework of the reef itself. This process contributed to the expansion and stabilization of reef environments. Over long periods, repeated cycles of growth and sediment deposition created thick layers of reef material. Early coral-like organisms that contributed to reef development included groups such as stromatoporoids and tabulate corals, which appeared in different geological periods. These organisms formed colonies with rigid structures that were capable of resisting movement from water currents. Their skeletal remains accumulated over time and formed large reef frameworks. These frameworks provided surfaces for additional organisms to attach and grow, increasing the size and complexity of reef systems. The growth of early coral reef systems was influenced by the availability of nutrients in the ocean. Nutrients such as nitrogen and phosphorus supported the growth of microorganisms that lived in association with reef-building animals. These microorganisms contributed to the cycling of nutrients within reef environments. The presence of nutrients supported higher levels of biological activity, which in turn increased the rate of reef formation. Areas with stable nutrient availability tended to develop more extensive reef systems. Light penetration in shallow waters also played an important role in reef development. Many reef-building organisms had relationships with photosynthetic microorganisms that required sunlight to produce energy. These microorganisms lived within the tissues of reef-building animals and provided them with energy-rich compounds. This relationship supported faster growth rates and allowed reef structures to expand more rapidly in shallow, clear waters where sunlight was abundant. The physical structure of early reef systems was shaped by the growth patterns of colonial organisms. Individual organisms within colonies grew in repeated patterns that created branching, layered, or massive structures. These structures were influenced by water movement, sedimentation rates, and biological interactions. As colonies expanded, they formed interconnected networks of skeletal material that reinforced the stability of the reef. Over time, these networks became thick and extensive, covering large areas of the seafloor. The early development of coral reef systems also involved periods of change in sea level. Changes in sea level affected the depth of water in reef environments. When sea levels were higher, reef systems could expand into new areas of shallow sea. When sea levels were lower, some reef areas became exposed or experienced reduced growth conditions. These changes influenced the distribution and structure of reef systems over time, leading to variations in their development across different regions. Reef-building organisms responded to environmental changes through growth patterns that allowed them to adapt to varying conditions. Some organisms grew vertically to reach areas with better access to sunlight, while others expanded horizontally across the seafloor. These growth patterns contributed to the overall structure of reef systems and allowed them to persist through changing environmental conditions. The accumulation of calcium carbonate from reef-building organisms gradually transformed sections of the seafloor into hardened reef structures. These structures provided stable surfaces that supported a wide variety of marine life. Many organisms lived on or within reef systems, including small invertebrates, mollusks, and early fish species. The presence of these organisms increased biological diversity in reef environments and contributed to the complexity of reef systems. In early coral reef systems, the interaction between living organisms and non-living materials was continuous. Living organisms produced skeletal material, while non-living processes such as sediment deposition and chemical precipitation contributed additional material. Over long periods, these combined processes created large accumulations of reef material that extended across significant areas of ancient seas. The development of reef systems also involved biological competition for space on the seafloor. Reef-building organisms competed for attachment surfaces and access to favorable environmental conditions. This competition influenced the distribution of reef structures and contributed to variations in reef density. Areas with favorable conditions tended to have higher concentrations of reef-building organisms, resulting in thicker and more extensive reef formations. Reef systems also served as environments where new forms of marine life could develop and diversify. The stable structures provided shelter and surfaces for attachment, allowing many organisms to live in close proximity. This proximity supported interactions among different species and contributed to the expansion of marine ecosystems. Over time, reef environments became areas with high levels of biological activity and structural complexity. The mineral composition of early coral reef systems remained relatively consistent, with calcium carbonate being the primary building material. This material was deposited in layers over long periods, creating solid structures that could persist for millions of years. The layering process was influenced by seasonal and environmental changes, which affected the rate of biological growth and mineral deposition. The early formation of reef systems also involved the gradual establishment of ecological relationships among marine organisms. Some organisms lived on the surfaces of reef structures, while others lived within internal spaces. These relationships contributed to the overall stability of reef systems by creating interconnected biological communities. Each organism played a role in maintaining the structure and function of the reef environment. As reef systems continued to develop, they expanded into different marine regions. The distribution of reef systems was influenced by ocean currents, continental positions, and local environmental conditions. Shallow continental shelves provided ideal conditions for reef growth, and many early reef systems formed in these regions. These areas supported continuous biological activity and allowed reef structures to grow over long periods. The development of early coral reef systems also involved gradual changes in the types of organisms that participated in reef building. Over time, more advanced coral groups appeared, contributing to increased structural complexity. These organisms had improved abilities to build rigid skeletal frameworks and maintain stable colony structures. Their presence led to the expansion of reef systems into new environments and increased the overall scale of reef development. In addition to coral organisms, other reef-building groups such as algae and sponges contributed to reef formation. These organisms produced additional skeletal material and helped bind reef structures together. Their presence increased the stability of reef systems and supported the continued accumulation of mineral material. The combined activity of multiple organism groups resulted in the formation of large and durable reef structures. The growth of early coral reef systems was a continuous process that depended on the balance between biological production and environmental conditions. When conditions were favorable, reef systems expanded steadily through the accumulation of skeletal material. When conditions changed, growth rates slowed, but existing structures often remained intact and continued to support marine life. Over long periods of geological time, early coral reef systems became widespread in certain marine regions. Their development influenced the distribution of marine habitats and supported the expansion of marine biodiversity. The presence of reef systems created stable environments where many organisms could live and reproduce, contributing to the overall complexity of ancient marine ecosystems. The early stages of coral reef development represent a long sequence of biological and chemical processes that operated continuously in ancient oceans. These processes involved the interaction of living organisms, mineral materials, and environmental conditions that together produced large and stable marine structures. The accumulation of reef material over extended periods resulted in the formation of extensive reef systems that became important parts of marine environments in Earth's early history. Marine life during the Devonian period existed across oceans that covered large parts of Earth, during a time span that extended from about 419 million years ago to about 359 million years ago. These oceans contained many living forms that filled different ecological roles in water environments. Life existed at many depths, from shallow coastal seas to deeper marine zones, and organisms occupied water spaces in ways that supported feeding, growth, reproduction, and survival. Marine organisms included vertebrates, invertebrates, and microscopic life forms that lived in water columns and on sea floors. These life forms existed under changing environmental conditions involving temperature shifts, ocean chemistry variations, and differences in oxygen availability within water layers. Marine vertebrates included fish that had skeletons made of bone and fish that had skeletons made of cartilage. Jawless fish were present and continued to exist in various marine settings. These jawless fish had body structures that supported simple feeding methods, and they lived in environments where they could access small particles suspended in water. Jawed fish also existed and developed different feeding structures that allowed them to consume a wider range of food sources. Some jawed fish had armor-like external body coverings made of hard material that protected their bodies. These armored fish had head and trunk regions covered with strong plates that supported defense and movement through water. Their body systems included fins that allowed directional movement and stability in marine currents. Cartilaginous fish also existed during this period. These fish had internal structures made of cartilage rather than bone. Their bodies supported flexibility and movement in water. Some of these fish had body shapes that allowed steady swimming in open water environments. Their sensory systems supported detection of movement and chemical signals in surrounding water. These fish occupied different marine zones and accessed food sources through active movement and feeding behaviors. Marine invertebrates existed in large numbers and occupied seafloors and reef environments. Brachiopods were present and lived attached to hard surfaces on the seabed. These organisms had shells made of two parts that enclosed soft internal tissues. Their feeding process involved filtering small particles from water. Brachiopods existed in many shapes and sizes and occupied many areas of shallow marine environments. Their shells provided protection from physical disturbance and environmental changes. Trilobites also existed in marine environments during this period. These organisms had segmented bodies with hard outer coverings. Their bodies were divided into sections that supported movement along seafloors. Trilobites had compound eyes that allowed them to detect light and movement in water. They moved across sediments and interacted with organic material present on ocean floors. Their feeding habits included consumption of small organic particles and other available marine material. Mollusks existed in many forms during this time. Gastropods were present and moved slowly across surfaces in marine environments. Their bodies were protected by coiled shells in many cases. They interacted with sediments and organic material found in coastal and shallow marine zones. Bivalves also existed and lived within shells composed of two hinged parts. These organisms remained attached or partially buried in sediments and filtered water for food particles. Their feeding process supported survival in areas where suspended particles were available in surrounding water. Cephalopod organisms existed and included forms that had external shells in early developmental stages of their evolution. These organisms had internal systems that supported movement through water using fluid expulsion. Their body structures included tentacle-like extensions that assisted in capturing food and interacting with the environment. Cephalopods lived in marine zones where they accessed active prey organisms and moved through different depths in water. Coral organisms existed in marine environments and contributed to the formation of reef structures. These corals lived in colonies composed of many individual units. Each unit contributed to the building of skeletal material that accumulated over time. Coral colonies existed in shallow, warm marine waters where sunlight reached water surfaces. These organisms supported reef formation that provided habitats for many marine species. Reef structures created spaces for feeding, shelter, and reproduction for multiple marine organisms. Sponges were present in marine environments and existed as simple multicellular organisms. Their bodies contained internal channels that allowed water to pass through. They filtered small particles from water for nutrition. Sponges attached themselves to solid surfaces on seafloors and reef structures. Their simple body organization supported survival in a wide range of marine conditions. Echinoderms existed in marine environments and included organisms with radial body structures. These organisms lived on sea floors and moved slowly across sediments. Their body systems included tube-like structures that assisted in movement and feeding. Some echinoderms attached themselves to surfaces using anchoring structures. These organisms existed in shallow and deeper marine zones and interacted with organic material available on ocean floors. Planktonic organisms existed in large quantities in marine waters. These organisms drifted in water columns and formed a foundation for marine food systems. Phytoplankton performed processes that involved conversion of sunlight into energy within surface waters. Zooplankton consumed smaller organic particles and other planktonic forms. These microscopic organisms supported energy flow within marine ecosystems and contributed to the feeding structures of larger marine organisms. Marine ecosystems included interactions between organisms occupying different levels of water environments. organisms living near the sea floor interacted with sediment materials and organic remains. Organisms living in midwater zones moved through water columns and accessed food particles and other organisms. Surface-dwelling organisms interacted with sunlight and atmospheric exchange processes at the boundary between air and water. These interactions supported continuous cycles of feeding and growth among marine life forms. Ocean environments during this period included areas where water movement influenced distribution of nutrients and organisms. Water currents moved suspended particles across marine regions. These particles included organic materials and mineral components. Marine organisms adapted to water movement patterns through feeding behaviors and movement strategies that allowed them to remain in suitable locations for survival. Sediment accumulation occurred in many marine regions and supported habitats for bottom-dwelling organisms. Marine chemical conditions included variations in oxygen levels within water layers. Oxygen availability supported respiration in many marine organisms. Some marine zones contained higher oxygen concentrations near surface waters, where interaction with the atmosphere occurred. Deeper marine zones contained different oxygen conditions that influenced organism distribution and activity. Marine organisms adapted their biological systems to these conditions through physiological processes that supported survival in available environments. Marine reproduction systems included various strategies among different organisms. Some organisms released eggs and sperm into water columns where fertilization occurred externally. Other organisms developed internal reproductive processes that protected early developmental stages. Larval stages of many marine organisms drifted in water columns before settling into suitable environments for growth and development. These life cycles supported distribution of species across marine environments. Marine biodiversity during this period included many forms of life that occupied ecological roles in feeding, reproduction, and environmental interaction. Organisms occupied surfaces of rocks, coral structures, and sediment layers. Some organisms moved freely through water, and others remained fixed in place. Feeding systems included filter feeding, predation, and consumption of organic material from sediments. These feeding systems supported energy transfer within marine environments. Marine fish diversity included species with different body forms and feeding strategies. Some fish had strong jaw structures that allowed consumption of active prey. These fish used movement abilities to capture organisms in water. Other fish had body structures that supported slower movement and feeding on smaller particles. Fish with armored body coverings had protective features that supported survival in environments where physical interactions occurred frequently. Marine habitats included reef systems that supported many organisms. Reef structures formed through accumulation of skeletal materials produced by coral organisms. These structures created complex spaces within shallow marine waters. Organisms used these spaces for shelter, feeding, and reproduction. Reef environments supported interactions between fish, invertebrates, and microorganisms. Marine sediment environments included areas where particles accumulated on seafloors. These sediments supported organisms that lived within or on top of substrate materials. Burrowing organisms moved through sediments and accessed organic materials present within them. Surface-dwelling organisms interacted with sediment particles during feeding activities. Marine life distribution extended across different oceanic regions, including coastal zones and open marine waters. Coastal zones contained environments influenced by land and water interaction. Open marine waters contained environments where organisms moved through large water spaces. These regions supported different forms of marine life that adapted to available conditions. Marine ecosystems during this period supported continuous biological activity involving feeding, growth, and reproduction. Organisms existed in interconnected systems where energy moved through feeding relationships. Primary producers existed in the form of microscopic organisms that used sunlight. Consumers at different levels fed on available organic material and other organisms. Decomposition processes occurred through microbial activity that broke down organic remains and returned nutrients to marine environments. Marine adaptation included development of structures that supported survival in various conditions. Some organisms developed protective coverings. Some developed movement structures that supported swimming or crawling. Some developed feeding structures that allowed filtering of water or capturing of prey. These adaptations supported survival in environments with varying physical and chemical conditions. Marine life forms occupied ecological roles that included feeding on suspended particles, predation on other organisms, and interaction with sediment materials. These roles supported distribution of energy within marine systems. Organisms interacted through feeding, movement, and reproduction within shared environments. Marine ecosystems included continuous cycles of biological activity. Organic material moved through food systems. Organisms contributed to environmental processes through growth and reproduction. Marine environments supported long-term stability of life through availability of nutrients, water movement, and habitat structures. Marine organisms existed in conditions that supported biological diversity across oceanic regions. These organisms occupied many ecological niches and contributed to ongoing biological processes within marine environments. Their presence supported continuous activity in ocean systems where water, nutrients, and living organisms interacted in sustained ways. The rise of jawed fishes began in the ancient oceans during a very long stretch of Earth's history, when marine life was already present in many forms. These fishes belong to a major branch of vertebrate life that developed a movable jaw structure which changed the way feeding and survival happened in water environments. Before this development, many fish-like animals had simple mouth openings without movable jaws, and their feeding depended on suction, filter feeding, or slow intake of small particles in water. Over long periods of geological time, changes in body structure led to the appearance of jaws supported by cartilage and later bone. This change did not happen in a single moment, but through many small biological steps across vast spans of time measured in millions of years. The earliest known jawed fishes appeared during the Paleozoic era, a very long division of Earth's history that spans hundreds of millions of years. The first clear signs of jawed vertebrates are found in rock layers that formed around 440 million to 410 million years ago. During this time, marine ecosystems contained many groups of living organisms, including early fish forms without jaws, shelled animals, and various small marine creatures that lived in shallow and deep waters. In these environments, body structures gradually changed through natural biological processes across many generations. The development of jaws in fish came from structures in the throat region that were originally used for supporting gills. These structures were made of flexible tissue and cartilage. Over time, parts of these gill-supporting structures shifted in position and shape. Some segments became stronger and gained movement that allowed opening and closing actions. This movement created the first forms of biting ability. The formation of jaws allowed certain fish to take in larger pieces of food and handle food items in a different manner from earlier fish forms. This change also affected feeding habits in marine environments, where different organisms interacted through feeding relationships. The internal structure of early jawed fishes included a skull made of cartilage or early bone material. The skull provided protection for the brain and support for sensory organs. The jaw structure attached to the skull through joints that allowed movement. Muscles developed around these joints to enable opening and closing actions. Teeth also appeared in some of these early jawed fishes. These teeth were simple in structure and were formed from hard tissue materials. They were arranged along the jaw edges and helped in holding and processing food. During the time when jawed fishes began to appear, oceans covered large parts of Earth's surface. Many shallow seas existed over continental regions, and deeper ocean basins contained a wide variety of marine life. Water conditions included different levels of oxygen, temperature variation, and nutrient distribution. These conditions supported many forms of early vertebrate life. Jawed fishes spread into these marine environments and occupied many ecological roles that involved feeding on smaller organisms and interacting with other marine life forms. The internal skeleton of jawed fishes developed in two main forms during early stages. One form was based on cartilage, a flexible and supportive tissue. The other form involved bone tissue that provided stronger structural support. These two forms existed in different groups of jawed fishes and shaped their body structure in different ways. The presence of cartilage or bone influenced how the body maintained shape and movement in water. The sensory systems of early jawed fishes included organs that detected movement, vibration, and chemical signals in water. These systems allowed them to respond to changes in their environment. The lateral line system developed along the sides of the body and contained sensory cells that detected water movement. This system helped the fish understand surrounding water currents and detect nearby organisms. Eyes were also present and allowed detection of light and shapes in the water environment. Smell and chemical detection systems helped locate food sources in the surrounding water. Jawhead fishes also developed paired fins, which included structures located on both sides of the body. These fins provided stability and movement control in water. The presence of paired fins allowed changes in direction and balance during swimming. Along with these fins, other fin structures located along the back and tail supported movement through water. The coordination of fins and body muscles allowed controlled movement patterns. The appearance of jaws created changes in feeding behavior. Jawed fishes could grasp, bite, and process food in ways that were not present in earlier fish forms. This allowed access to a wide range of food materials such as small marine organisms, soft-bodied animals, and organic matter found in water. Feeding actions involved opening the jaw, capturing food, and closing the jaw to hold or process food before swallowing. During the early stages of jawed fish development, different groups began to appear. One group included cartilaginous fishes which had skeletons made mainly of cartilage. Another group included early bony fishes which had skeletons made of bone tissue. These two major groups developed in different directions, while still sharing the basic jaw structure. Both groups continued to develop over long periods of time in marine environments. Fossil evidence of early jawed fishes is found in sedimentary rock layers formed in ancient seas. These fossils include jaw fragments, teeth, scales, and sometimes partial skeletons. The preservation of these remains allows study of their body structure and development patterns. Fossils show that jawed fishes were present in many marine environments across different regions of the ancient Earth. The evolution of jaw structures involved gradual changes in cartilage elements that were originally part of the gill system. These elements shifted position and gained new functions related to feeding. The upper and lower jaw structures formed from these modified elements. The connection between jaws and the skull became more stable over time, allowing controlled movement. The muscle system supporting the jaws also developed in coordination with skeletal changes. Muscles attached to jaw elements allowed opening and closing actions. These muscles were controlled by nerve systems that coordinated movement responses. The development of these systems created a functional feeding mechanism that operated through coordinated muscle contractions. Early jawed fishes also showed changes in body covering structures. Scales developed in many groups and provided protection for the body. These scales were made of hard materials and varied in shape and arrangement depending on the fish group. The skin beneath the scales contained sensory cells and blood vessels that supported body functions. The circulatory system of jawed fishes included a heart that pumped blood through blood vessels. Blood carried oxygen and nutrients to different parts of the body. Gills were used for extracting oxygen from water. Water passed through gill openings, and oxygen entered the bloodstream, while carbon dioxide was released into the surrounding water. Reproductive systems in early jawed fishes involved the production of eggs and sperm. Fertilization often occurred in water environments. Eggs were released into water and developed outside the body. Some groups showed variations in reproductive methods, including internal fertilization in certain lineages. The development of reproductive strategies supported survival in different marine environments. As jawed fishes continued to appear in various marine habitats, their body structures showed gradual diversification. Some forms developed elongated bodies while others had broader body shapes. Fin structures also varied in size and position. These variations allowed occupation of different ecological roles within marine systems. During the period around 400 million years ago, jawed fishes became more common in marine ecosystems. They were present in shallow coastal waters, reef environments, and deeper marine zones. Their presence influenced feeding relationships within these ecosystems, as they interacted with many types of marine organisms. The skull structure of jawed fishes included openings for sensory organs and muscle attachment points. The brain was protected within a cavity in the skull. Nerves extended from the brain to different parts of the body, controlling movement and sensory responses. The organization of the nervous system allowed coordinated actions during feeding and movement. The development of cartilage-based skeletons in some jawed fishes allowed flexible body movement. Cartilage provided support while allowing bending and motion. Bone-based skeletons provided firm support for body structure and muscle attachment. Both systems supported different ways of movement and body control in water environments. The early diversification of jawed fishes included forms that lived near the ocean floor and forms that moved through open water. Bottom-dwelling forms interacted with sediments and organisms living on or near the seabed. Open water forms moved through water columns and interacted with drifting organisms and currents. The structure of teeth in jawed fishes varied in shape and arrangement. Some teeth were pointed, while others were flattened or arranged in multiple rows. Teeth were replaced over time as they wore down or broke during feeding. The continuous replacement of teeth supported feeding activity throughout life. Jawed fishes also developed specialized feeding structures in some lineages. These structures included modified jaws and teeth adapted for specific feeding behaviors. Some forms developed strong jaw muscles for holding prey, while others developed fine structures for filtering food particles from water. The brain structure of jawed fishes included regions responsible for sensory processing, movement control, and basic behavior responses. Different parts of the brain processed signals from eyes, smell organs, and lateral line systems. This allowed coordinated responses to environmental changes. The body shape of jawed fishes supported movement through water by reducing resistance and allowing smooth motion. Muscle segments along the body contracted in waves, producing movement from head to tail. Fins adjusted direction and stability during movement. Environmental conditions in ancient oceans included changes in sea levels, water temperature shifts, and variations in oxygen content. Jawhead fishes adapted to these conditions through gradual changes in body structure and function. These changes occurred across long periods of time, measured in millions of years. The fossil record of jawed fishes continues to provide evidence of their early development. Fossils are found in different parts of the world, showing their wide distribution in ancient marine environments. These fossils include remains of skeletons, teeth, and body impressions preserved in rock layers. The interaction between jawed fishes and other marine organisms involved feeding relationships where energy and nutrients moved through marine ecosystems. Jawhead fishes consumed smaller organisms and were also part of larger feeding systems involving other marine animals. Over long spans of geological time, jawhead fishes developed a wide range of forms. Some retained simple body structures, while others developed more specialized features for different environments. These changes occurred gradually through many generations. The nervous coordination between sensory input and muscle response allowed jawed fishes to respond quickly to environmental signals. This included detection of movement, light changes, and chemical signals in water. Responses involved swimming actions, feeding behavior, and avoidance of obstacles. The skin and scale structures of jawed fishes also provided interaction with water movement. Scales reduced direct impact from water flow and offered structural support. Skin layers contained cells that supported growth and repair. The respiratory system of jawed fishes remained based on gills throughout their development. Water flow through gill structures allowed continuous gas exchange. Gill filaments provided surface area for oxygen absorption and carbon dioxide release. Jawhead fishes continued to diversify across marine environments, occupying many ecological roles and developing varied body structures, feeding systems, and sensory abilities across long geological periods extending through the Paleozoic era and into later stages of Earth's history. The dominance of armored fish called placoderm was a major part of marine life during a long part of early vertebrate history, especially during the Devonian time on Earth. These animals lived in seas, rivers, and many water environments that existed many millions of years ago. Their presence shaped how marine life developed, how food systems in water functioned, and how early jawed vertebrates spread across different habitats. The group of armored fish called placoderms appeared in a world where life in water was already diverse, but still developing in structure, form, and ecological roles. Their bodies carried hard outer coverings that protected important parts of their internal systems, and this protection played a central role in their ability to survive in different aquatic environments. Placoderms were jawed fishes, meaning they had structures in their mouths that allowed them to grip, hold, and process food in ways that earlier jawless fishes could not. The presence of jaws created new feeding methods and allowed placoderms to use a wide range of food sources found in marine and freshwater systems. Their jaws were often supported by strong bone structures connected to the head shield. The head shield itself was part of the armored covering that extended across the front of the body, giving protection to the skull, brain area, and gill regions. The rest of the body in many placoderms was covered with plates that formed a protective layer. These plates were made of bone material and were arranged in segments that allowed some movement while still providing protection. The development of these armored features was linked to the biological changes taking place in early vertebrate evolution. During the Devonian time, many aquatic animals were developing new structures, and placoderms became one of the most noticeable groups in these environments. Their bodies were supported by internal skeletal systems that allowed movement in water, while the outer armor provided structural strength. The combination of internal support and external protection made them stable in different water conditions, including shallow seas, river systems, and coastal waters. The internal organs of placoderms were positioned within the armored sections of their bodies. The head region contained the brain, sensory organs, and feeding structures. The armored plates around this region formed a protective casing. The gill structures were positioned behind the head shield, allowing water to flow through for respiration. The body region in many placoderms contained muscles that supported swimming movements. The tail region in some forms was less armored, allowing greater flexibility for movement in water. Placoderms appeared in fossil records from early periods of the Devonian world, and their remains show that they were widespread across many regions of ancient seas. Fossil evidence has been found in what are now different continents, showing that they lived in many environments that existed during that geological time. The distribution of placoderms across these regions suggests that they adapted to different water conditions, including warm shallow waters and deeper marine environments. Their ability to occupy various ecological spaces contributed to their presence in many fossil layers. Feeding behavior in placoderms was connected to the structure of their jaws and teeth-like bone plates. Some placoderms had sharp cutting edges formed from bone plates that allowed them to process hard food materials. Other forms had flattened structures suitable for crushing or grinding food items. The variation in feeding structures allowed different placoderms to use different types of food resources in aquatic environments. The presence of these feeding adaptations played a role in how they interacted with other marine organisms in the same environments. The growth of placoderms involved the expansion of their armored plates as they matured. Young placoderms had smaller body structures, and as they developed, the armored sections became more extensive. The growth process involved the deposition of bone material in layers, forming stronger protective coverings. The skeletal system inside the body also developed in coordination with the external armor. This allowed the fish to maintain mobility while increasing structural protection. Reproduction in placoderms involved internal biological processes that are understood from fossil evidence of certain species. Some fossil findings suggest that certain placoderms gave birth to live young rather than laying eggs. Evidence of embryo-like structures inside fossilized bodies has provided information about reproductive development. This shows that placoderms had complex reproductive systems that allowed internal development of offspring in some species. The presence of such reproductive systems indicates a level of biological development that supported survival in different aquatic conditions. The sensory systems of placoderms included organs that detected movement, vibrations, and changes in water conditions. The head region contained openings and structures related to sensing the environment. These sensory features allowed placoderms to respond to surrounding conditions in water environments. Vision systems were present in many species, with eyes positioned in the head region, allowing detection of light and movement. These sensory abilities supported feeding, movement, and interaction with other aquatic organisms. The internal structure of placoderms included a backbone-like arrangement that supported the body. This structure was less complex than later vertebrate groups, but it provided necessary support for movement and stability. Muscles attached to this internal framework allowed movement of the tail and body segments. The coordination between muscles and skeletal support enabled placoderms to navigate through water environments and maintain position in different aquatic conditions. Placoderms occupied different ecological roles in marine systems. Some species lived near the bottom of water environments, where they moved across sediment surfaces. Others moved through open water areas and interacted with different parts of aquatic systems. Their presence in multiple ecological zones allowed them to use available resources in different ways. The armored structure of their bodies provided protection from environmental conditions in these habitats, including pressure from surrounding water and contact with surfaces. Fossil evidence shows that placoderms had a wide range of body sizes and shapes. Some had broad head shields and short bodies, while others had elongated body forms with extended tail regions. The variation in body structure reflects adaptation to different environmental conditions in water systems. The bone plates that formed their armor were shaped in different patterns depending on the species, and these patterns provide information about their classification in paleontological studies. The environment during the Devonian time included extensive water systems that covered large areas of the planet. These systems included shallow seas, river networks, and coastal regions where many aquatic organisms lived. Placoderms were present in many of these environments and contributed to the structure of marine life communities. Their armored bodies allowed them to occupy ecological roles that involved feeding, movement, and interaction with other aquatic organisms. The development of placoderms occurred during a time when vertebrate life was undergoing significant changes. Zooid structures were becoming more common among fish groups, and placoderms were among the early groups to show these features. Their jaws were connected to skull structures that supported feeding mechanisms. The arrangement of bones in the head region allowed controlled movement of the jaw structures, enabling different feeding actions. The fossil record of placoderms includes preserved body parts such as skull plates, jaw structures, and body armor segments. These fossils provide information about their internal and external anatomy. The bone material used in their armor was capable of being preserved in sediment over long periods, allowing researchers to study their structure millions of years after their existence. Fossilized remains show details of plate arrangement, joint connections, and structural design of their bodies. Placoderms existed in environments where water conditions varied across different regions. Some habitats had calm water conditions, while others had moving water currents. The armored structure of placoderms provided stability in these environments. The distribution of weight across their bodies allowed them to maintain position in water systems while performing feeding and movement activities. The development of jaw systems in placoderms involved bone structures that supported biting and holding food. The jaw mechanisms were connected to muscles that allowed movement. The structure of these jaws varied across different species, showing diversity in feeding strategies. Some had strong biting structures, while others had more flexible arrangements for handling food materials. The decline of placoderms occurred after long periods of presence in aquatic systems. Changes in environmental conditions and biological development in other fish groups affected their presence in later periods. However, during their time of dominance, placoderms occupied many ecological roles in water systems. and contributed to the development of vertebrate life in aquatic environments. The study of placoderms provides information about early vertebrate development, especially in relation to armored body structures and jaw systems. Their fossils continue to provide data about the arrangement of bones, the structure of protective plates, and the organization of internal systems. The preservation of these features allows detailed examination of their biological characteristics. Placoderms also show variation in head shield structure. The head shield often covered the front portion of the body and extended over key internal organs. This shield was made of hardened bone material, arranged in plates that fit together in a structured form. The design of these plates provided protection while allowing necessary movement for feeding and sensory activity. The tail region in many placoderms was less heavily armored, allowing movement through water. The muscles in this region played a role in propulsion. The movement of the tail allowed placoderms to navigate through different aquatic environments and maintain position while searching for food or interacting with surroundings. The development of sensory canals in placoderms included structures that detected changes in water movement. These canals were located along parts of the head and body and provided information about environmental conditions. This system helped placoderms respond to movement in water and detect nearby objects or organisms. The bone material in placoderm armor contained layers that formed during growth. These layers provide information about age and development patterns in fossil specimens. The structure of these layers shows how the armor expanded over time as the organism developed from early stages to full maturity. Placoderms existed in ecosystems that included many other marine organisms, such as early sharks, bony fish, and invertebrate species. Their presence contributed to the structure of these ecosystems through feeding activity and movement patterns. Their armored bodies played a role in how they interacted with physical conditions in water environments. The head and jaw structures of placoderms show complex bone arrangements that supported feeding functions. These structures were connected to internal skeletal systems that provided stability. The coordination between head armor, jaw bones, and muscle systems allowed controlled feeding activity. Some placoderms developed specialized feeding structures that allowed them to process specific types of food materials found in aquatic environments. The variation in these structures reflects the diversity within the group. Fossil evidence shows differences in bone arrangement across species, indicating a range of biological adaptations within the group. The study of placoderm fossils continues to provide information about early vertebrate anatomy and the development of armored body systems in aquatic life. The preserved remains show details of skeletal structure, plate formation, and internal organization. These findings help build understanding of how early jawed vertebrates functioned in aquatic environments over long periods of Earth's history. The presence of placoderms in different fossil sites across the world indicates that they were part of many aquatic ecosystems during their time. Their remains are found in sediment layers that represent different water environments, showing their widespread distribution. The preservation of their armored plates allows reconstruction of body structure and biological features that existed during their time in ancient waters. Their biological systems included coordination between skeletal structure, muscle movement, and sensory input. These systems work together to support feeding, movement, and interaction with environmental conditions. The armored structure remained a defining feature throughout their existence, shaping how their bodies functioned in water systems. Placoderms represent a significant part of early vertebrate life in aquatic environments, with their armored bodies and jaw structures forming an important stage in biological development within marine systems. The continuation of placoderms in ancient aquatic systems shows further details about how their bodies functioned over long spans of time and how their internal and external structures supported survival in many different water environments. Their biological systems continue to develop in complexity across many generations, with gradual changes appearing in bone structure, jaw arrangement, and body proportions. These changes are recorded in fossil layers that represent different periods of early vertebrate history, especially during the Devonian time on Earth, which stretched from about 419 million years ago to about 359 million years ago. Placoderms continued to show strong development of armored plates that covered the head and front parts of the body. These plates were not random in structure, but followed specific growth patterns based on the species and its environment.